Today, in the last class, we talked about energy and how we have kinetic energy, rest mass energy. Remember that energy is the total energy of an object. Is E total is equal to gamma mc squared. And we can divide that into two parts. We can divide that into a kinetic energy plus a rest energy. The rest energy is equal to mc squared, and the kinetic energy is equal to gamma minus 1 times mc squared. And part of the motivation for dealing with energy is that we want to have an analog to momentum that has to do with space, the x, y, and z coordinates, rather than with time. If you recall, the momentum principle can be written as that the sum of the external forces acting on an object or on a system is equal to the change in momentum. And I should make this that the sum of the forces acting on a system over some period of time, delta t, is equal to the change in momentum of the system. And that system can be one object or it can be a whole bunch of objects. It would be nice if we have some sort of analog to that is of the form the sum of the external forces on a system acting over some distance r, over some displacement of the system, is equal to the change in some property of the system. And that property is the energy of the system. Okay? So this can be, like I say, it can be one particle. Up here, this is the energy of one particle, one mass, not of a system. We have the sum of the forces, and we have distances that are changing the energy of the system. Now, if these forces act over some distance, this change in energy of the system is going to be, of course, the final energy after this force is exerted minus the initial energy. And that may include a change in the kinetic energy of the system. You know, like you push on something and it moves faster. We'll talk about that a lot. Seldom do we see cases where we exert a force on something and its mass increases, its rest mass increases. So many times in these types of situations, the rest mass, the rest energy is not going to become a factor at all. We can just get rid of it. Okay, so the whole point of this then is we're going to develop the idea of energy and try to understand what this term means, what forces acting over distances are. We have a term for this. We call this work. And work has units of joules, just like energy has units of joules. So let's start talking about what work is. Later on, we'll actually prove this statement in special cases. So work. In high school, you probably heard this as force exerted over distance. The two operative terms are the force and the distance. Notice the force is a vector. This is a vector. Work actually is a scalar, has no direction. Let's see, suppose I take a box. There's a box. I'm holding up the box. I'm exerting a force on it. It's not moving. Even though I'm exerting a force on it, I'm not moving it up, down, anyway, so I'm not actually doing any work on this. I can only do work if the object moves, and it can move up or down. And notice that if you think about it, I'm not the only agent exerting a force on this object. There's also gravity involved. So if I take a mass, in this case there's my hand exerting a force upward. There's gravity, mg, pulling downward. Those are both forces acting on the mass, but they only do work if the mass is moving in some direction, some displacement delta r. Okay. Weight is equal to mg. Alright, but it's not quite so simple as that, because nothing ever is. I have to consider how the delta r, the vector, is related to the vector that is exerting the force vector. And I can get in situations where I can consider the total work done on the object, I can consider the work done by this force or the work done by that force, and then add them up to a total sum. Okay, so I'm going to define what work is in all of its full glory. Work is equal to a force dot producted with a displacement, and this is a vector dot product. It's sometimes called an inner product. You may have seen this in your math classes, but let me review it real quick. Suppose I have a vector f is equal to f of x, f of y, f of z. These are the three components of f. And delta r, that's a displacement, has three components: delta rx, delta ry, delta rz. Then the dot product of those two vectors is f of x times delta rx, f of y, excuse me, I wrote this wrong. The dot product is equal to f of x delta rx plus f of y delta ry plus f of z delta rz. And that's equal to the work done by the force F acting over a distance r. Notice this is a scalar. There's no direction involved in it. All of these are just numbers. These are just the three components of the force and the direction. So that's how you would calculate this work scalar if you were doing forces and direction in terms of a vector. We'll work out this in detail later on. There's another way to express a dot product that involves angles, drawing the vectors and making angles between them. So I will erase this. Suppose I have a force that's going off like this, a force vector, and let me put in the object just to emphasize that there is some physics in here, not just math. So there's the force vector, there's the object, and I'm going to have the object move a distance delta r, a displacement, from the initial position to the final position. And there's an angle between those two, which I'll call theta. The work done by this force in moving to this angle is equal to the absolute value of the force times the magnitude or absolute value of the displacement times the cosine of that angle between the force vector and the displacement vector. That turns out to be equivalent to the vector notation I did before. Comes out with the same answer. Sometimes it's more convenient to look at work done in this notation. Sometimes it's more convenient in the other notation. Okay. Let me give you an example. Let me remind you, before I do an example, that whenever you work a work and energy problem, you have to do the same things that you did for momentum problems. You have to draw a picture of whatever the system is. You have to define the system. You have to draw in the vectors, label the vectors, make sure you know what the directions are, and only then can you start writing in the equations to try to find out what parameter you want. So for instance,